and in the school. And during this conference, we will develop and design cities, architectures, morphing ecologies, which may go back to an anthropologic era. We are spanning and interweaving around what Buckminster Fuller coined as Spaceship Earth. And this year's topic for eCAADe, Anthropologic, Architecture and Fabrication in the Cognitive Age, from smart to behavioral, from digital to material, touches upon what we would like to call the cognitive digital turn. Or to say it with Richard Breutigham's words from 1976, I like to think of a cybernetic ecology where we are free of our labors and joined back to nature, returned to our mammal brothers and sisters, and all watched over by machines of loving grace. This year's topic implies ubiquitous computing, artificial intelligence, augmented reality, material intelligence, but to mention a few. The resulting design strategies overwhelm our discipline of architecture, encouraging a rethinking of architecture, the architect's role and responsibility as well, and this is what we are discussing over the next 1.5 days, architectural education for the global architects for the 21st century. Now, before I give the word over to my colleague Dietmar and then to the director of the Institute of Architecture, Professor Misselwitz, I would like to introduce you to a few logistic things. We will live stream the morning session with Professor Williams, and we will also live stream the evening sessions with the architect Lars Krückeberg and Professor Spiegelhalter from Miami. These streams will be also shown through the WebEx portal that we have introduced. We will be able to take questions from the WebEx audience. However, we will not be able to tune you in with your voice or your video. The reason is basically of technical nature. So with this small introduction, I would like to pass over to my colleague Dietmar, who would introduce the subject in more depth than I just did. Thank you very much.
So, good morning, everybody. I know that's for some people quite early, I guess also in China, for example, at 3 a.m., but why actually anthropologic? This term refers to, on the one hand, to a new geologic period, the Anthropocene, and on the other hand, to an interdisciplinary discipline involving humanities and social sciences and natural sciences. We can also define it as a science of humans, especially the study of human beings and their ancestors through time and space, concerning physical character, environmental and social relations, and culture. For us today, architecture. According to Elizabeth Gross, architecture has the capacity to both extend man's destruction of the environment, but also, at its best, but much more rarely, it retains the capacity to invent new modes of coexistence, more sustainable ways of living, and more aesthetically pleasing experiences of inhabitation. Matteo Pasquinelli goes even further by referring already to the automation of the Anthropocene. An interesting quote to this eCAADe and also to last year's eCAADe in Porto, which was addressing the fourth industrial revolution. According to Bernard Stiegler's thesis, who sadly passed away this August, technology has always impacted evolution and the social structure of societies. It is essential to understand that what Stiegler seeks is not merely rethinking the relationship between humans and machines, but machines themselves as a challenge to thinking and philosophy itself. The technological relationship between humans and machine rests on the capacity to adapt. The adaptation itself, of course, is a central human ability, and also occurs in our interactions with software as well concerning the topic of the conference, anthropologic architecture and fabrication in the cognitive age, from smart to behavioral, from digital to material. Coming back to Gross, we need to develop new modes of coexistence with machines and human beings, more sustainable ways of living, and more aesthetically pleasing experiences of inhabitation. Is this not an excellent description of what we as architects can do, and also a perfect topic for a fruitful debate in the next 2 days? This debate would not have been possible without the help of the eCAADe community, the Keynote, the authors, the peer reviewers, and especially the TU Berlin team, and as well as our sponsors. Thank you. I will hand over now to Philipp, the director of the Institute of Architecture, TU Berlin.
Yeah, thank you to Liss and Dietmar, dear colleagues and friends of eCAADe. The Institute of Architecture at TU Berlin, which I'm representing here, is deeply honored to host the 38th conference of eCAADe. As director of the Institute, I have the honor to welcome you officially, dear contributors and participants from all over the world who are now tuned in, and the few who sit here in this room, to join us for a really super exciting debate over the next 2 days. Let me start by expressing again why I feel that this conference makes an essential contribution to research and education in architecture. Architecture, as we know, is a cultural practice of central importance to society, reflecting and shaping our values and visions of how we want to live together on this planet. But architecture has always been, as was said before, deeply intertwined with technological advances. It is in architecture that we engage with creatively transferring, embedding, and unfolding science and technology into culturally appropriate, equitable, and sustainable environments across multiple scales, beginning with materials, rooms, buildings, neighborhoods, to cities and regions. To make sure that technology actually helps us in advancing towards this betterment of societies rather than hindering us, as we know it has done multiple times in the past, to build beautiful and functional environments that are sustainable in the multidimensional sense of the world. I'm referring here obviously to the ecological and social dimensions of sustainability in particular, that are ethical, just, and inclusive, forward-looking, as well as building upon the experiences of the past. As academies, we are ideally positioned to discuss this across different generations, particularly with students and new talents in research that are often much more agile and curious about technological advances than we are. We are pleased that almost 1,100 students in this building are studying with us now, often digitally, each year to ambitiously and courageously tackle present and future challenges through architecture. eCAADe is obviously particularly concerned with digitalization. Digital culture, digital architecture, and digital manufacturing have become drivers of our decision-making in architecture and urban design, have affected the tools we use and the forms and functions we design with. Anthropologic architecture and fabrication in the cognitive age, the topic chosen for this conference rather appropriately, allows us and you as researchers, students, educators in the field of computational architecture to locate our research practice and teaching in a paradigm of architectural transformation and human, or rather humanity-focused reflection of architecture on the other side. The topic also allows for, let's say, encourages us to work and design with the United Nations Sustainable Development Goals that have been set and that form a very broad and integrated framework and definition for sustainability and transformation towards sustainability. Now, this conference has been deeply impressive in the making over the past half a year, I would say. I learned from Prof. Werner that more than 500 abstracts from all over the world have been sent in and went through a peer review cycle. 145 papers have been identified, which you will be able to listen to in short contributions. You will also be able to indulge in 7 keynote contributions, roundtable discussions at the conference, and obviously also actively engage through the formats that Prof. Werner explained. I've also seen already the super impressive 2 volumes of conference proceedings that have been compiled, and this amazing digital navigation tool, rather appropriate for the topic of this conference, that the organizers have composed and put together. I've never seen anything like that it will help you for the next 2 days to pick and choose wherever you want to contribute. So what's left for me is to really thank the organizing committee of this conference, above all, Prof. Werner and Dietmar Koering, my colleagues here from TU Berlin, but also the entire eCAADe task force, and the Berlin technical team that sits here in the background that makes this whole event possible under conditions of Corona. I also would like to thank the German Research Foundation and the Friends of the TU Berlin who have generously supported this conference, and really wish you a fantastically interesting and inspiring time. Thank you.
Thank you, Philipp, for the wonderful introduction, and also Liss again. We will now continue with the opening keynote of Chris Williams. One magician in the coexistence between humans, engineering, and algorithms is Chris Williams. Chris is a professor at Chalmers University, Sweden. Chris' research hinges on the relationship between geometry and structural action as applied to towers, bridges, and fabric and shell structures, as well as the response of these flexible structures to the wind. His work in the generation of structural form through biological and other analogies has led to the collaboration on projects including the Frei Otto Multihalle in Mannheim, the British Museum Great Court Roof by Norman Foster and Associates, or the Gardens by the Bay glass houses in Singapore by Grant Associates and Wilkins and Iyer. He has worked personally in his career with Ted Happel and Ove Arup, and with his practical and academic approach, Chris has probably influenced generations of young architects and engineers. Hence, we could not think of anyone else than Chris for today's opening lecture for the eCAADe conference with the title Anthropology and Computers. Is it possible not to be depressed in the age of multinationals? We welcome Chris. Great that you made it. Wonderful.
Thank you very much, Dietmar. Let me begin by starting my computer. Okay. Are you connected to my computer? Yes. Oops. Okay, there we are. Now I'm going to try and see if I can get my phone connected to my computer as well, so I don't have to move about so much. Okay, there we are, fantastic. Well, first of all, it's fantastic for me to be back in Berlin in this difficult time of coronavirus. And you can see the title of my lecture is it possible not to be depressed in the age of multinationals? And I suppose I could have added Corona into the title. I think I'll discuss this question. I'm not sure whether I'll be able to come up with any answers, but at least it's worth talking about. And of course, some people can be depressed even when everything is going well for them, and there are other people who are able to be happy even in the most difficult circumstances. For us in the UK, we are particularly depressed at the moment by Brexit. And one of the things I want to do is to apologize to all our friends in Europe for the appalling behavior of our Prime Minister. So anyway, that's something that's depressing us in the UK at the moment. I suppose I should really apologize perhaps about coming to Germany and then talking to you in English. But of course, as you know, English didn't start in what we now call the United Kingdom. It actually started in the north of Germany. So maybe that's not so bad. Now, I suppose one of the reasons I get asked to these sort of conferences is because I'm so old, and I can remember a time before, I guess, any of these companies existed. And I started work before any of these companies existed. And I suppose the question that I'm asking myself is how we exist as individual human beings and individual communities in a world which is dominated by these multinational companies. And in particular, what that means for us as architects and engineers. I'm actually an engineer myself, but I think that the distinction between architecture and engineering is very blurred. It's perhaps even more blurred now in the new digital age. So if we take, for example, Revit, one of the big questions that we have to ask ourselves in academia is that better? Okay. One of the questions we have to ask ourselves in academia is, for example, how much time we should spend teaching our students how to use software such as Revit, because for our students, when they go out into industry, the skills in being able to use software like this is understandably highly prized. People in industry don't want to spend time teaching young engineers and architects how to use software like this. And of course, the problem is that this software is horrendously expensive, criminally expensive. And of course, companies like Autodesk give students free licenses at university to encourage them to use their software. And then, of course, once you know how to use that particular piece of software, then in a sense you are locked into using that software, because to learn to use somebody else's software would take you too much time. And so, in a sense, you are a prisoner of, in this case, Autodesk. But of course, it's not just Autodesk, it's other companies as well. So I'm just raising that as an issue, which is perhaps something we can talk about later. And alongside this, of course, is the question of the skills and knowledge that we have as human beings, and the way in which we interface with each other and with computers. And one of the things which I think is changing is the question of, excuse me a moment, of the things which are considered to be easy or difficult, highly skilled or not particularly skilled. So, for example, the radiologist on the bottom right, one would have thought is an extremely skilled occupation, and I'm sure that it is. But it is an area which it is relatively easy to apply artificial intelligence, in the sense that you can scan the image into a computer, and the computer can perhaps learn through neural networks and artificial intelligence of various sorts to look for the telltale signs of tuberculosis or lung cancer or whatever it is. On the other hand, the young gentleman on the bottom left has just assembled an IKEA chair, which you would have thought is not a particularly skilled occupation. But those of you who've worked with robots, for example, know that to actually get a robot to assemble an IKEA chair is an almost impossible task. The two upper images show a London taxi, and on the right is a man or a woman doing what's called the knowledge, which is where, at least in the past, and maybe still even today, London taxi drivers had to memorize thousands, maybe tens or hundreds of thousands of streets in London, so they would know how to get from this place to that place. And the question now, of course, is whether a skill like that is at all relevant in the age of sat-navs. And I suppose in a way it's quite sad that that skill is no longer relevant. Now, I think it's very important for us to remember that even though these days we rely on computers, that this is a relatively new phenomenon, and so many interesting and beautiful objects, buildings, bridges, aeroplanes, cars, were designed without computers. People would do drawings, as you know, on drawing boards. The woman on the top right there is using a slide rule, which is a sort of analog computer. And when I started work at Arup in the early 1970s, we all had those. We didn't have electronic calculators even in those days. You can see the French curves in front of her, used for drawing curves. And these objects were not only interesting and beautiful, they were, some of them, incredibly complicated. So, for example, on the bottom right, we see the radial engine out of the Lockheed Constellation airliner there. And engines like that are at least as complicated as anything we design these days using computers. So even though we use computers, and it would be ridiculous to say that we should stop using computers, we should remember the culture and the knowledge of people in the past who were able to work without computers. I hope I'm not a Luddite. Luddites were a group who attacked machinery, factory machinery, because it was seen to be taking their jobs. So one has to be very aware of that and to look to the future positively rather than just say look back to some sort of idyllic past that maybe never existed. So how does one use computers? Well, we use computers in so many different ways. I suppose one good thing about using computers is that there are a relatively small number of agreed languages which have an ISO standard, International Standards Organization standard. And that means, for example, that if you decide to do something using these languages, then you can communicate with other people in other countries and other cultures, independent largely of the control of multinational corporations. It also means that if you do something in these languages, that that something is something that will endure, in the sense that, well, we'll come to talk about the British Museum Great Court, but the software I wrote for the Great Court was written in C, or C++, and that software can run on any computer now without buying any commercial software. It will continue to run in 20, 30, 100 years' time, whereas the chances are that if you do something very deeply embedded in some commercial code, in some commercial application, then maybe in a year's time or 2 years' time or whatever, that software will cease to function. This is just a list of automobile manufacturers in France. It doesn't necessarily have to be France. It could be Germany, it could be America, it could be anywhere. So there are, here we are, 2 pages of it with 4 columns in each page. The only current manufacturers are Citroën, Peugeot, and Renault, and DS, which is part of Citroën. And all these other companies were born and died, which is sad. So they are, if you like, they're extinct in the same way that an animal or a plant might become extinct. In terms of, if you like, diversity, we have lost diversity, and that's something which is perhaps a shame. So eccentric cars such as this no longer have a place in today's world, which is much more uniform. So that Volkswagen don't make the Beetle anymore; they make the Golf, which is essentially the same as the equivalent Peugeot or Toyota or whatever. So that's something which is inevitable. It's not part of some massive conspiracy. It's just something that we should be aware of and maybe do what we can to encourage diversity. Now, one of those car manufacturers that are no longer with us is Voisin. I just chose that because it was Le Corbusier's choice of car. And here he is with the car, with his wife, and also with Josephine Baker. And I've chosen to include this image, which is modular. And Le Corbusier drew that picture, or so it says in the caption, on board the ship Vernon S. Hood. Now, this sort of image tells us, of course, that the application of geometry and mathematics to architecture is not something that's new. And of course, it wasn't new in the time of Le Corbusier. But it's nice to look at images such as this and try and relate them to computers. Now, in this image here, the black is the original image by Le Corbusier, and the red is superimposed upon the black using software that I wrote. So this is the code. This is the entire code written in C++. Now, of course, you could do this in lots of other environments. You could do it in Revit, you could do it in Grasshopper, you could do it in so many different ways. And to a certain extent, it's very much up to us as individuals to use whatever platform that we want for this. But because it takes time and effort to learn to use a particular platform, we tend to not move about too much. The way this program works is it does various calculations, and you may be able to see sines and powers and things like that in there. The way the drawing was done was by writing a text file and those lines towards the bottom where it says Madeline, which is the name of the text file. So a text file is written, it's a DXF file, which of course is an AutoCAD standard. But fortunately, DXF files are openable by almost every piece of software. So in a sense, even though DXF is an AutoCAD standard, it is an international language which we can all use. The modular is based on the Fibonacci sequence, and I won't spend time now talking about the maths, although it's always much nicer to talk about maths than other things. But I think at this stage I'd like to mention the Padovan sequence, particularly because it's named after an ex-colleague of mine, Richard Padovan, which is the next one along, if you like, from the Fibonacci sequence, which gives the golden ratio, and the Padovan sequence gives the plastic number. And certainly, if you're interested in this sort of thing and how it may be applied to architecture, then I suppose what I'm thinking of is that there is a certain simplicity and elegance to this. And if you want to incorporate this into architecture, then in a way you want to do that in a simple and elegant way, and as far as possible not get it buried in some mammoth piece of software. Maybe I'm being, as I said, a bit of a Luddite in that. So I'll now talk a bit about some projects that I've worked on. Dietmar mentioned the Multihaller. I was extremely lucky to work on this project because I was only in my early 20s. So I worked with Ian Liddell and Ted Happold at Arup, and we'd come across to Germany from time to time to meet with Frei Otto and other people. And this project is still standing, and there's a debate at the moment, of course, about what the future for this project will be, but that's something that is not for us to discuss now. So that was in the mid-1970s, the Multihaller project. So 25 years or so later, I worked on this project with Foster & Partners, Bureau Happold, and Wagner Bureau, who were the steel and glass contractors. Quite a lot had changed in those 20 years. We did use computers for Mannheim, but in a very limited way. But by the time the middle 1990s came around, we were using computers a lot. And this was the first project that I'd worked on where we exchanged drawings via computer. So the software I wrote would produce a DXF file, which I would then email to Foster & Partners. Or sometimes I'd email the code to Foster & Partners, and they would run the code to produce a DXF file, which Philomena Russo, who was the architect at Foster's, would then open in MicroStation. So that seemed to work quite well. And essentially, it's very similar to the way that people work these days. Dietmar also mentioned this project, which is Gardens by the Bay. Grant Associates were the landscape architects in Bath, Wilkinson Eyre, the architects, and Atelier One, who are a small firm of engineers in London, were the structural engineers. Another project more recently in Melbourne, again with Atelier One, was the Chadstone Shopping Centre. We worked in very much the same way on this, again using text files to communicate the information. The software I wrote for this, which Atelier One then took over and modified, was actually written in processing, which was a very popular software platform for architects until Grasshopper came along. Okay, so I've mentioned history a little bit, but I guess it's good to discuss it a bit more explicitly. So those of you who are interested in architectural geometry are of course aware that it's part of a very long tradition going back, well, I suppose to the start of humans as animals. As an academic discipline, it certainly goes back 500 years or so. This is from a book on stereotomy by Leroy from 1862, and on the right it shows a picture of an ellipsoid shell, and of course the question there is how much you need to know about geometry in order to design a shell like this. Clearly Leroy knows an awful lot, because this picture shows a system of principal curvature coordinates which involves an intersection of ellipsoid with hyperboloids of one sheet and hyperboloids of two sheets. And again, on this image, the red is produced by me using a computer program, and you can see that this drawing, produced entirely by hand, is unbelievably accurate. So even though, of course, today we wouldn't dream of producing a drawing like that without using computers, it was possible to do it by hand. Earlier than that, there was the book and the works of Philipp Delorme. This is Anne. So that's 500 years, or nearly 500 years ago. So I think it's important that we as architects and engineers think of ourselves as being part of a long tradition, and that really what's happened in the last 20 years or so is that some of the stuff that we used to do has been automated, but that's it, it's just been automated. So it bears the same relationship, so computation in architecture bears the same relationship to actual design as, say, word processing corresponds to literature. This is the Hotel de Ville in Arles, which many people find particularly inspiring because it is so simple and so elegant. And I don't think there are many of us who could produce something as beautiful as that, even with all the tools that we have at our disposal. Other example, the Grand Palais in Paris. Structures like this are unbelievably beautiful, and it's just amazing to think that how people were able to produce these projects using just drawing boards and slide rules and so on. Now, in the area that I work, which has largely been in shell roofs, there are a number of people who I suppose are particularly inspiring. There was a golden age in the construction of shell structures with people like Felix Candela, Taroja, and not so well known, in fact I didn't discover him until fairly recently, Amancio Williams from Argentina. And the reason that I find his work particularly inspiring is that there's a simplicity about these umbrellas which makes them particularly, I don't know what the word is. There's something about them anyway. It's like a piece of Bach or something like that. There's something about them which is particularly appealing. And I'm going to try and explain to you why that is. But before coming back to that, I'm just going to talk a little bit about Fry and Ted. Now, one of the reasons that Ted was so successful was that for Ted, one of the most important things about the design process was that it should be enjoyable. And that's why so many engineers came to work for TED, is why so many architects wanted to work with TED. It was very, very important to TED that the design process should be enjoyable, and that if you weren't enjoying your work as an engineer or as an architect, then you couldn't really produce good work. And I think that's a very, very important thing which we should remember now. And when we think about the way that we work, the software we use, and so on, it's partly about succeeding in business and making sufficient money to live and so on, but it's also about enjoyment and whether we enjoy the work that we're doing. Friotto was very inspired by the work of Darcy Thompson, Darcy Thompson, who was a biologist, a mathematical biologist who studied the structural and physical behavior and evolution of plants and animals. And so you can see a shell there, you can see a spider's web, which was very much the inspiration, I suppose, for Friotto with his tension structures, such as the Munich Olympic Stadium. And of course, you probably all know that Fry was very much interested in using physical models as the design process. So he'd build hundreds, thousands of physical models and test them and measure them and use those in the design of real buildings. So this brings us back to the multi-haller, which is a timber grid shell. And this image here shows the structure being load tested. I could talk for hours about the issue of the structural behavior of this project and trying to ensure that it stood up and didn't fall down. But that's another issue. In terms of the design process, we relied very much on physical models, and this is the model that we made in our office in Soho in London. The roof was made of timber laths, which were laid out flat and lifted up on scaffold towers using a forklift truck. But the physical model was a very important part of the design process, and physical models are still potentially a very important part of the design process. We loaded the physical model with nails and then scaled those results to predict the behavior of the full-scale structure. And the scaling of model tests is very easy to do, but actually very, very few people know how to do that. But it means that you can build quite a simple model, such as that, and predict how a complex structure such as this will behave. It behaves very much in the way that a sieve behaves. So that's just a common kitchen sieve. And you could take one of those and put a few bags of sugar on it, and from that you could predict how a grid shell would behave. It wouldn't be as accurate as a computer analysis, but it would be more reliable in the sense that the potential for error is very much reduced. This shows the timber joints, and this shows the hanging model that Friotto made to determine the shape. The idea being that the hanging model is hanging purely in tension. You invert that to produce a pure compression structure. And this, of course, was not a new idea. It goes back to the time of people like Hooke. It was used by Gaudi. This is a recreation of the model for the Colonia Güell. And talking about computers, this is the computer that we used for the structural analysis for Mannheim in conjunction with the physical model tests, CDC 6600, which cost about $7 million in those days, but is much, much, much less powerful than a mobile phone is today. This is another model that we used for Mannheim, and this was the erection model. It's made from a wire mesh, and there are weights hanging from it, fishing weights, and that was to scale the flexibility of the mesh as it was lifted up into shape. So it's not an analysis of the finished object, it's an analysis of the building process. And again, we learned things from that model which you would find very, very difficult to obtain even today from the most sophisticated computer program. So physical modeling is still potentially useful. Right, okay. So now back to the Great Court, which, as I said, was designed in the mid to late 1990s. We deliberately decided that we didn't want to go for sort of NURBS-type surfaces and so on, because they're not very satisfactory in many ways. And instead, we decided to go for an analytically defined surface, defined by these functions. The advantage of having analytically defined surfaces is that they have a certain purity, which you don't have from NURBS. And also, in the case of this surface, there's a singularity at the corners. The curvature is actually infinite as you approach the corners, but I won't talk about that in any detail. Since the roof was built, quite a few research students have studied it, because it's a nice project to study, because in a sense it's so simple in that it involves a circle and it involves a rectangle. And there are many different ways in which you can cover that space between the circle and the rectangle. There are also many different grids that you can put onto the surface. So it's nice to take simple problems and study those. There is one thing about the roof which is perhaps worth mentioning, and that is that if you look closely on Google Earth, you can see that there are trusses on the outside of the roof in each corner. And we wanted, when I say we, Bureau Happold wanted to put a tension structure inside the roof in order to resist the horizontal thrust from the roof. The roof is sitting on sliding bearings, and so the only horizontal thrust is at the corners, which is resisted by a tension in the edge element. The architects, Foster and Partners, didn't want to have any tension structure inside the roof. And so to get over that, we had to put this massive truss, or these massive trusses, on each corner. The forces in these trusses are so big that they had to be machined out of solid steel rather than made from tubes or whatever. Now, the question there is, it's an interesting philosophical question in terms of honesty and integrity. I think Foster's are probably right in the sense that the roof works best without having anything inside to distract the eye. On the other hand, there is perhaps a lack of honesty in that in order to understand how the structure works, you need to know that there are these trusses on the outside. So that's an interesting question. Now, we're also interested in more natural forms. So this was a study I did with Atelier 1 for a grid shell using a grid that was based on a dragonfly wing. And on the right is a more recent project that we did with UCL and Imperial, the University of Bath, a study for a multi-story building. That shape there is based on conformal mapping, which is a technique using complex numbers. And the entire structure is defined by just one mathematical function. So in principle, at least, if you took one small part of that surface, you could then grow the rest of the surface from that. There's no discontinuity in terms of curvature anywhere. Computation in engineering and architecture involves all sorts of areas. This is a fluid mechanics study that I did some while ago. I think I'm getting a bit short of time now. Is that right, Dietmar? So I haven't talked about analysis very much in my talk, but analysis is something which for us engineers is particularly relevant. Now I'm just going to finish off by going back to the Amancio-Williams shells. Now, Candela built many hyperbolic paraboloid shells, and this shell is made up, it's an umbrella structure with a square plan made up of 4 hyperbolic paraboloids. The hyperbolic paraboloids have folds between them, which are the red lines, and on the upper drawing there's a fold between the hyperbolic paraboloids and a horizontal plane, and that's given by the blue line. Now, those folds are there in real life, together with the curvature of the shells. The upper drawing is what's known as the area stress function, and that drawing tells you the state of horizontal stress within the shell. So the state of stress is described by the upper drawing, and the geometry is described by the lower drawing. So this is an example of what's called graphic statics, where you relate geometry, as in drawings, to structures. And the red folds correspond to a concentrated compression in the shell, and the blue folds correspond to a concentrated tension. So that's how a Candela hyperbolic paraboloid shell works. This is work that we're doing with Masaki Miki in Tokyo, Bill Baker and Toby Mitchell at SOM, and Emil Adils and Alexander Schultzholm at Chalmers in Sweden, where I work. This is the maths that goes with all that stuff. The nice thing about maths is that it's very beautiful in its own right and is completely sustainable in that it doesn't involve any money or any materials. This was produced using latex, which is much better than Word. Anyway, so go back to the Amancio-Williams shells, and what we're trying to do is to replicate the work that Candela did for his shells by, if you like, sculpting the Z, which is the shape of the real shell, and sculpting the shape of the stress function, which describes the state of stress in the shell. So what you're doing is you're doing, if you like, a piece of sculpture using mathematics, where you're not only sculpting the physical object, you're also sculpting the state of stress. And what you're trying to do is to relate those two things together. And this is something that I did last week using processing, trying to combine all these things together within one piece of code. Now, I don't know how we're doing for time. That's the end of my talk, and I can talk about this in more detail or anything else that in more detail. I can show you some software running if you like, but I think it's probably best for me to stop now. And Dietmar, I don't know what's going to happen now. Are there going to be some questions?
Yeah, right.
Okay.
We'll have a small discussion.
Okay. So, and it's 10:30. Was that the time I was supposed to?
Perfect timing. Yep.
Okay. Great. So, thank you very much, everybody. I hope you've been able to hear me. Okay. So, I'll go and sit.
Just going to sit down here.
You'll sit down. Okay.
Just gonna get you some more water.
More water would be nice. Yes.
leave the bottle here.
Okay, thank you.
Yeah, thank you, Chris. Wonderful lecture. I really enjoyed it, and well, especially I guess in my age, I have to say that when I started studying architecture around 2000, I mean, it was just in the awakening somehow to use Rhino 1 and 2 first kind of softwares, and I think it's really impressive. I mean, that we don't forget the past, right? How certain things were developed. Especially you elaborated on the Multihalle, Mannheim, by Mutschler, Frei Otto, but also if we look at other buildings like Saarinen and that stuff, what has been possible also without computers. So sometimes it's a question, you know, now we have all those tools, we can be more accurate and everything, but sometimes personally I feel creativity somehow develops in another way. Can you just maybe talk a little about what has changed in the last 30 years of this relationship? I mean, certain points you have addressed already in the lecture, but maybe the better question would be, what can we change actually in the current education of young architects and engineers?
Right, okay. Well, I suppose the first thing to say is that we're always constrained by the environment, I mean the cultural environment, the economic environment, and so on within which we work. So if you're designing a building or a bridge or whatever it is, you obviously have constraints in terms of the site, the amount of money that you have available to you, the brief and so on. And you're also constrained by the knowledge and the expertise that you have, together with the software that you have available to you. I suppose it all boils down to tools that you use. So obviously, if you're making things, you have various tools. You have planes and saws and spanners and machine tools and so on, cranes. If you're designing something, you have tools which in the past would have been a drawing board, a pencil, model making and so on. And now you have digital tools. What you make is determined by the tools that you use. And so, well, for example, in car design, you can look at the shape of car bodies over the last 20, 25 years, from the time when people like Bézier and de Castelnau at Renault and Citroën would first developing CAD tools, that the shape of car bodies evolved as the tools to design them evolved. The ability to put creases into the body and so on. So cars these days still have a lot of creases, whereas 20, 30 years ago they didn't have creases. So I guess we just have to accept that the way we design is influenced by the tools we have available. And the problem is that in a way it's subconscious, because perhaps you know how to do certain things in a particular piece of software, and so naturally you modify your design to use the things that you know how to do. If there's something you don't know how to do, then you say, well, let's leave that out of the design. I suppose because we're all using the same software, then that will mean that to a greater or lesser extent, design becomes more uniform, apart from any other sort of cultural influences. I suppose it's also a question of power. I mean, in the sense that the more you, I mean, if you make your own tools, if you're, say, a Japanese carpenter and you make your own plane, then you have complete control over the tool that you use. If you write your own software, then in a way, have more control over what's going on than if you use somebody else's software. On the other hand, it doesn't make sense for us all to go away and write our own software for word processing or basic structural calculations and so on. So, and there isn't time to go back to use many of the old hand methods. So in a way, there's no obvious way out of this, except to say that what does seem to happen is that software is always changing, so that at the moment everybody is using this software or that software. But in a few years' time, that software will be replaced by something that's newer and better. What it'll mean, of course, is that there's perhaps a generation of young architects and engineers who are learning, say, Revit now, and then in 20 years' time, when they're in their mid-40s, something new will come along, and all the young engineers and architects will be using this new stuff, and the old people will be feeling a bit redundant because they don't know how to use the new stuff. So there are all sorts of issues like that. I mean, I know quite a few engineers and architects who, because they're now in their mid-careers, they feel that they're past learning the latest software. And that firms are taking in a new generation of people who are really up to date with the latest stuff. So there's all sorts of issues like that. And it's important to be aware of them, but that doesn't necessarily mean that we should become depressed.
Oh, I agree, yeah. But maybe it's also to think about, like with this, if we call it a buzzword, AI, I mean, I would say 10 years ago, everybody was talking about smart geometry. Now we talk about AI and how this might change the future workspace and that stuff. So would this enable more creativity, or is it more if we see AI as a, let's say, guideline, as a co-pilot for the design process and engineering?
Okay. Well, in the UK, with COVID, we abandoned all the school examinations this year. And so they were replaced by an algorithm which took all the information about each school, each pupil in school, and decided what results these pupils will have. And as a result, which university they could go to and so on. But there was a tremendous hoo-ha because it was discovered that this algorithm unintentionally gave particular advantages to people from more wealthy backgrounds. It was not intended, but it just happened. So this algorithm had this very unfortunate effect, and as a result, there's a tremendous fuss, and the results from the algorithm were then completely ignored, and they went back to the teacher assessments. So that meant that in the UK, at least for a few days, there was a tremendous discussion about computer algorithms and their power and so on. And of course, we're used to them. We're used to the fact that, say, if you want to borrow some money to buy yourself a new bicycle, you don't go to speak to the manager in the bank and he or she decides whether you can buy your bicycle. You know, computer algorithm does the same. Computers are very good at doing things which are repetitive and correspond to simple rules. So I mentioned the example of radiology. Driving a car, I suppose, is a sort of interesting case because it's both very mechanical thing to do, but also under certain circumstances, value judgments have to be made. And there's, of course, all this discussion about, you know, what should the car do if it has the choice of killing the occupants or killing a pedestrian, and so on. But I think in engineering, we're very used to the fact that the thing that that took most of our time, which was doing structural analysis, is now no longer something which you do by hand. It's causing a crisis in education, because the question is, do we need to teach young engineers to be able to do these hand calculations or not? But it's a very mechanical thing, and to a certain extent, it's a very deterministic thing. Other things, like in architecture, for example, if you're, say, planning people movement through a train station, that is something that you can do with algorithms, and it's quite common now. Of course, there is the question of whether architects will lose the ability to actually be able to plan their buildings, and instead they'll rely on the computer to work out all the pedestrian flows and so on. The same thing, of course, could apply to, say, aesthetic judgments, so that architects and engineers are very much concerned with aesthetic judgments. And of course, one could imagine the situation where you come up with a proposal and then you just say, well, computer, can you analyze this for me? And say, is this beautiful or not? And if the computer says it's ugly, then you say, oh dear, sorry, and they need to change it. So, and of course, all sorts of issues where everything is a compromise. In society, there's a compromise between freedom and responsibility. There's always a relationship between the advantages of one group of people against another group of people, and so on. And I think the problem is that if we rely too much on AI, then we're relying on algorithms where quite possibly nobody understands what the algorithm does. The algorithm may have been written 20 years ago by somebody who's no longer around. Yeah. And so we are, in a way, I think it's something like Trump and Johnson as not really human beings. They are sort of almost like cyborgs, if you like. So the worst thing you can imagine is that by relying on artificial intelligence, you produce something like Trump, who in a sense is like an artificial intelligence. He's not like a human being.
Well, I agree. I guess that's the reason why certain people already speak about the algorithmic governmentality, right?
Yeah.
So, but I think it's a very hot debate which needs to be continued soon, and hopefully also to certain papers during this conference who address this topic, because we might run out of time, but we probably have also a further discussion. If you have time, maybe this evening on the stage, it would be really great if you can join. We will also have this evening Thomas Spiegelhalter and Lars Krückeberg, which is really great to have them here. And we will now probably continue with the conference. I just have to make a few announcements that we have around one keynote by Rachel Armstrong. Not sure if you have met her already, but she will be online. She will speak about certain topics about cell structures and architecture. But before we start with the keynote of Rachel, it's actually also a little announcement by the eCAADe Council and the President. Normally this happens traditionally wise also in the opening session, but we have to decide to move this during the lunch session, because at 12:01 this is the best global timing for everybody to be awake somehow. So in this sense, we are looking forward to this opening. And last but not least, I really would also announce that we also have this year the Ivan Petrovich Award for Young Architects. That means, and researchers, that everybody who is under 35 and applied and submitted here with the paper is urged really to name his name and age to the moderator of the track if he wants to participate. It's really important. I think it's a great prize and a big honor to receive that. And this is at the moment, due to the online conference, the only way how we can manage that. So please, if you're under 35 and interested in it, talk to your moderator during the chat. And last but not least, we have not received any questions over WebEx from the audience. So I hope that we're going to have a bigger discussion over lunch and tonight. But overall, thank you for your yeah, I mean, that will come later. The Mouse Eisley Bar, of course, we're going to have an online party location, which is really great. It's open now already, so everybody can join, exchange. So we have at least a virtual social event, also supported by nice live acts this evening. But overall, thank you, Chris, that you made it to Berlin. I mean, I know it's a big effort to come here, especially in these times, and I think it's for all of us an interesting experience with this amazing audience all over the world.
Thank you very much, Dietmar.
Thank you. So there was, I close this session, and see you later at 1.